Okay, so let me just summarize what we discussed the one-dimensional random walk, and we basically said so on the lattice. And then we said we wrote an equation for okay, and then we cited, kind of generalized it to something like okay. So this is a random walk which takes a right step with probability p by 2, left step with probability p by 2, and has its weights with probability 1 minus p. Okay, and then we said that so you can do various limits. So if you take the limit of time continuous, then this equation basically, then you define time as some n tau. So each time steps takes some time tau, and then in the limit that tau going to 0, p going to 0, and p by tau finite, it gives you an equation which is del p equals to some rate into now this is p of x. X is still discrete. So when I write capital X, it's discrete variable, and small x is continuous variable, and this is now time. And this was defined as the discrete Laplacian operator. So it's just like a second derivative. And then we said that if you make space continuous, in both time and space, then you get the diffusion equation. Okay, there's also one other case you could have studied, which I'm not doing. You could have made time discrete and space continuous, so that's also possible. Okay, so and then so sort of one of the most important property of the random walk, it's like so this you can think of like if you have a large number of them, then so then it describes like if you put drop of ink in water, how does it spread, right? So what you'll see is that it's the size of the, so if you do this experiment and take some water and put a drop of ink, and you'll see that its size, which is r, grows as root t. Right? So that's one of the most important properties of a random walk, which is like x square is equal to n. And this is easy to, it was easy to prove. So this is what we call diffusion. Okay, so now we'll do this in, do the same thing in higher dimensions. Okay, so let's start with, let's say, 2D lattice. And this random walk starts from somewhere, and okay, so this is the origin, and after taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, it reaches some place. Okay, so so this we call now the x-axis, and this is the y-axis. So after 10 steps, it's reached 1, 2, 3, 4. So x is 4 and y is 0. Okay, so now the first question you can ask is like, what happens to this? And this is pretty, okay, so what is the random walk? At each step, it takes a step which can be either, it goes to one of the nearest neighbors. And you can define various random walks. You can also say there's a random walk maybe which goes here with some probability, here some probability, here some probability. I mean, it can go to the next term, diagonal term. And or it could move a little bit more also. So as long as the steps are chosen from a distribution which is short range, you will still get the same answer. So that's one thing. But we restrict ourselves to cases where it can go to one of the 4 neighbors. So, and in D dimensions, one of the 2D neighbors. So okay, so then of course, so the now we'll call x bar is equal to, let's say, x and y. This is the position of the walker after n steps. Okay, and so then x n bar equals to x n minus 1 bar plus a vector z n bar. So each step is a unit vector which can take 4 possible values, right? So in this case, I n bar can be either 1, 0, minus 1, 0, with probability. So, so after n steps, you just iterate this, so you just get n bar, and then again each step. So each size, this is I1, this is I2, this is I3, and each of them is an independent variable. So we can immediately write xn bar average is of course 0, and xn square average is, again we do the same thing we did before. N equals to, we break the, so it's a double summation and we break it up into 2 steps. So total number of steps is capital N, so this is x. Bar, and this we can write as again average of. Okay, so again, what is this? This is equal to, this is 0, and this is, each of them is 1, right? It can take, I mean, every time is in square is always 1. And so 1 into 1/4 plus 1 into, so it's 1. So this is 1. And this one is 0. Right? Because again, these are uncorrelated, so you can take average. And on an average, each step is in all 4 directions with equal probability, so average is 0. So so clearly this is true. In any dimensions, you can do the same thing. This is always true. It's always n. And the other thing you should notice is that, I mean, I could have made it more complicated. For example, I could have said that maybe this is okay, maybe this is 1/8, and it can also go to all these other 4 neighbors. Okay, so all these neighbors with equal probability. So I can also allow something like 1. So this point is 1, 1 with probability 1/8. So this is also a possibility, but then if I do this, I mean, it's is it still the same answer, or is it still n, or is it different? Huh? It shouldn't be same, but I mean, okay. So, no, it's not same, I think. Huh? Okay, so we have to. This will change, right? And this is still 0, because on an average, each step you can go in any direction, so its average is 0. So this is 0, but this is what is the answer for this? So it's all of this is 1. So 1 into 1 by 8 into 4 of them, and plus 4 into each step xi square is 2. 1 plus 1, 2, right? Xi square is 1 square plus 1 square, so that's 2. So 2 into 1/8. So that is half plus 1. So that's 3 by 2. Okay, so therefore it will be, for this model, xn square, it still grows as n, but the prefactor is 3 by 2, right? So, I mean, obviously, because now in each step you're jumping a bit more, so the diffusion constant should be larger. So it's still diffusive, so it still grows linearly with n, but it has a larger diffusion constant. And you can write a more complicated thing where you can take more like further steps of larger size, and basically the diffusion constant will keep increasing. Okay. And then you can imagine that you have a distribution where the second moment, so like each step is chosen from a distribution where the second moment is what determines the diffusion constant, right? So you can imagine a distribution where the second moment is infinite. Okay. So do you know what these are called? Levy, yeah. So there are things called Levy walks, where again it's the same model, but each step you take from a distribution which has very long tails. Okay. So in that case, it's not diffusive, right? So it will diverge, and then so those are like you get super diffusion or some things like that. Okay, so but we'll stick to diffusive models. Okay, so this is just a digression. Okay, so this is the easy thing to check. Okay, so now we want to find not just the moments, but the distribution. Let's say P of n. Okay, so now first we can try the combinatorial method. Okay, so what will we do now? We want to do the combination. So what is the probability I am at some point xy? So like we did the 1D combinatorial thing. So here, what should we do now? Huh? No, so forget the 4 possible. So let's forget this case. So okay, so we'll stick to this case only. So if we want to do this that binomial thing in now, so what should we do? So there we said we take, if you want to go to a particular place, it consists of some number of left steps and some number of right steps, right? Now you have up and down steps, right? So basically you have left steps, right steps, up steps, and down steps. And then what are the constraints? I want to reach x and y. No, x square plus y, x bar is xy. I mean, x square plus y square is not constant. I mean, x and y, it's a fixed point, x and y. L u plus t equals, yeah. R minus L is equal to x and u minus y. Okay, so and then what should we do? So it's the probability of each path is how much? 1 by 4 to the power n. Right, and then the number of combinations I can get doing LRUT is n factorial divided by okay, and so now of course the problem is what? Yeah, so there are 4 variables L, R, U, D, and only N3 constants. Right? So then finally you'll get a So you have to sum it over all the possible things which satisfy these constraints. Right? So you have to sum over all L, R, U, D satisfying these three constants. So obviously this looks difficult. Okay, so so it turns out that in this particular case, actually you can get a closed form expression. So okay, let me just do this before. So what you can do is you can do a trick, which is right here. Okay, so this is the square lattice, and now what you can imagine. So this is the origin. So now just imagine that you have another. Another sort of rotated lattice which looks like this. Okay, so if you look at this line, this is given by let's say u equals to x minus y, and this axis is given by, what is this axis given by? This is like x minus y equal to 0. Sorry, this is x equal to y. This is x equal. This is x equal to y, right? This line. So okay, so this is x minus y equal to 0. So this is x minus y, sorry, and this is x plus y. Okay, so I can construct this other lattice, and let's say these are the lines. Okay, so now if you look at, so every time the walker moves from, let's say, here to here, on this lattice, what does it do? On the green lattice. So on the white lattice, it's doing a random walk like that. Right? So in this other lattice, what is it doing? It's also doing a random walk, but on a slightly different, like the paths are, the jumps are on what? On diagonals, right? So it's like when the walk moves here on this lattice, it's actually not going to, it can't go here, so, but it can go on it's going on the diagonals basically. Okay, so okay, so now if so that means every time u can go to so uv can go to like u plus minus 1 and v plus minus 1. So these are the 4 jumps it can take. Okay. Unlike xy, so xy could have taken things like, it goes to x plus 1 y plus minus 1 y, or x y plus minus 1. Like this in the original lattice. But in the new lattice, these are the allowed jumps. Okay, so now what you can do is you can think of this as like 2 independent 1D random walkers. Okay, u and v, each of them is like a random walk. Okay, so therefore in this new coordinate system, the final okay, so okay, so let me just write down the answers. Okay, so I mean, in this case, because of this mapping, it's basically looks like a product of two random walkers on this U and V lattices. Okay, so, I mean, for every, uh, I mean, every trajectory on this lattice, you can basically obtain by like two independent 1D trajectories. Okay, so therefore, I mean, for the 1D random walk, you know, okay, so here x plus y, you should think like U, and x minus y is like v. So then I'm just writing the 1D results, right? 1 by 2 to the power n times something, and 1 by 2 to the power n something else. So it's just product of these two. So that's the final answer which you can get. Okay, so this thing works only in 2 dimension. Beyond 2D, you can't get exact result. So now we'll try to use the other method that we talked about, so which is using this Fourier transforms. So, so in this case, so which will work in all dimensions of the method of, or Fourier series, because we are on a lattice. So first P of x bar. Okay, so or at any point you can come from 4 different places. So so and each is with probability 1/4. So this is I mean the same equation that we wrote for the 1D case. So was this clear to everyone? This thing, at least kind of clear, right? I mean, if it's almost clear, it's okay, and then you can just you have to think about it. I mean, like probability is something here. I mean, you just work out like a few explicit pictures, then it becomes clear. But it's at least you can get more or less you can see what is the basic idea. I mean, using this mapping, then it becomes simple. So now, of course, this is the most straightforward method, which will always work in any dimension. So you just write the time evolution equation for the probability. And so then what should I do if I want to do a Fourier series? Huh? What? Continuum? No, I don't want to do the continuum limit. I mean, we want to do everything on the lattice. So what? Subtract p x n minus 1 and then? No, that will go to the continuum limit, right? I mean, that we don't want to go to the continuum limit. Fourier, we want to solve by Fourier series. I see, that's what I said, right? I mean, if you do all that business, you'll get here. And of course, even this you have to solve somehow. And that you have to, how do you solve this? But there was some way we solved this equation, right? So we should try exactly the same thing. So how did we solve this? By Fourier series. So what did we do? Right, and so there what we did for the 1D case is, so 1D we did we defined a new variable theta n, which is like sum over x. Theta, right, so so from x we transform to a new variable theta. It's like doing a Fourier transform, right, from x to k. Okay, so now what should we do? Two variables, so we should just generalize this, right? So we should probably have what, theta 1, theta 2. So theta 1, theta 2, so now n is equal to px, and this is x1 theta 1 plus. So it's just a two-dimensional Fourier series. It's like doing a two-dimensional Fourier transform. Okay, and so this is now sum over x bar. So it means x and y. So all points on the 2D lattice. Okay, so now again we do the same business. I mean, so just multiply by e to the power bar and sum over all x. This entire equation. Okay, and this gives, of course, this is what we call as P tilde. So this is P tilde. Theta is now a vector which has two components, theta 1, theta 2, and each of them is an angle variable. N is equal to, okay, so now we have to do this thing, and so if you look at this object, we are multiplying by e to the power I x. So x is a vector with two components, each of them are integer numbers. X and y both are integers numbers from minus infinity to infinity. Right, so x1 theta 1, okay. So, okay, so now I want to do x theta 1 plus y theta 2 times, let's say this term, let's try to understand this term, p of plus 1. Okay, so now obviously what I should do is try to make it x plus 1. So I have to put x plus 1 here and take out a minus theta. So this gives e to the power minus I theta 1 and then sum over xy. Right, okay, and now x plus 1 is like a dummy variable, I can just call it x. And so this is just p tilde. So this is e to the power minus I theta 1 p tilde x 1. Okay, so this I did for this term, and I can do the same for all these terms. And so then I would get so what are the four terms I'll get? So one term is this one. The one then. Huh? Then. And then. Okay, so therefore now again it's once in this Fourier thing, it's easy, right? Because in time, it's just like recursion. So if you know n minus 1 is related to n, and then you can just keep doing this, and you immediately get p tilde power n is equal to cos. Okay, and then this will of course depend on initial conditions. So okay, so this is the inverse of this. Sorry. No, what? X bar. This one. Oh, sorry. No. Oh, sorry, this was P tilde. This one, sorry. Okay, yeah, so this is, okay, so from here, I mean, at time n equal to 0, so we are, again, this is a delta function because we start from the origin. So this is at t equal to 0, this is again delta x bar 0. So both x and y are 0, so you get 1. Right? So that, so this object is again 1. So then this is what we, so we just plug in this thing in here. So this is okay, is it? No. This one. This, oh. Okay, so P of, versus cos. Okay, so this is the okay, so now this is it. So here again, this looks difficult, but what you can do is cos theta 1 plus cos theta 2, you can write as some cos theta 1 minus theta 2 and cos theta plus 1 plus theta 2, right? And then you can again rotate the theta 1, theta 2 coordinates and define, so instead of theta 1 minus theta 2, so you define as theta 1 tilde and tilde. If you make this transformation, then you can actually do the integral easily. Okay. And if you do, you will get it back that exactly that figure. So I won't do this the integral. You can check. Okay. So now, obviously, this is. I mean, easy to extend to any dimensions, right? I mean, so I won't do the details. I mean, so the final answer you can immediately write down any dimension. So D is the dimension. So now X bar is, let's say, X1, So what should be the answer? I mean, given this and what we saw for 1D, you can write the 3D answer, right, immediately. So what will be the generalization of this? 1 by to the power D, and obviously there should be D integrals. D theta 1 minus pi. And then this should just be replaced by summation cos divided by so this should be what now? I think it should be or you can, okay, it's better to put the D inside maybe. Okay, so right now we won't do anything else with this formula. I mean, this you can't, 3D and all, there's no analytic expression for this. You can't do the integrals. Okay, so one thing to again remember is that if you are really looking at a coarse grained level, then like if you are looking at scales where you don't see this spacing, like these are like, let's say, really small, then you can go to this continuum limit, and in always you get basically the diffusion equation, right? So for any dimension, basically you'll always get, if you go to the same continuum limit of x and time, then this is always true, that it gives you the diffusion equation. So this is the d-dimensional Laplacian. So this is always true. Okay, so at least some features are always true. I mean, like it spreads diffusively, and it's a Gaussian, or more or less a Gaussian, except at the tails and so on. Okay, so but now we look at things which are kind of different in and on the lattice, and you really need to work on the lattice. Okay, so for many questions, I mean, it's actually, you can just use this. Is much simpler, right? You can solve it. You always get a Gaussian distribution. You don't get anything so complicated. And so for many purposes, this is good enough. Okay. But for many questions, you really have to stick to the lattice. And this Polya problem is one such problem where you have to work on the lattice. Okay, any questions? Oh, is it okay? I guess you can always cook up a walk which looks like any independent random walk, and then it will be like that thing. But this, I mean, like here in 2D, you could map the 2D guy to such a thing. That in 3D you can't do. I mean, you can't do the mapping, but you independently you could have considered a walk which looks like, I mean, like I guess in 3D, if you have a cubic lattice and you move along the diagonals, it would be like that, I guess. 1, 1, minus, yeah, so all possibilities, yeah, then it would be like that. No, but that's a different random walk. So I'm saying in 3D, okay, so if you start with, okay, now it's difficult to draw, but if you start with the cubic lattice, and so here I started with the square lattice, and I said you can map it exactly to another lattice where it's moving on the diagonals, only diagonals, right? Now in 3D, you cannot do that. So you can't map the cubic problem to 3 independent random walkers. What you can independently do is you can consider another random walk model where it moves only along the diagonals. Okay, this is not, here we could map the two. So there you cannot map, construct an exact map between the two. You can always consider another such in walker, but those are like two different things which one is not related to the other. I mean, again, like at large scales, you don't care. It will, both will look diffusive and so on. But in questions of details, they will be different. 3D. No, so there's no exact closed expression in higher D. Only in 1 and 2D you can write. But in 3D you can write like this integral expression. And then you can get some asymptotic results made. Not, okay, I mean, there are people who keep trying to actually obtain this. I mean, I'm saying it can't be done exactly, but maybe you can, someone can do the integral like using some clever method. So, I mean, there are of course people who just work on trying to do that. I mean, but right now I don't know. Okay, so now we move to this this polyar problem. So first I'll just introduce something called generating functions. So this generating function is, I mean, actually, if, like if some of you are in from condensed matter, it's actually like a Green's function in some sense. Okay, so now what is it? I mean, so basically you define for given a probability distribution like this, P of x bar n, I can define this generating function. Okay, so I mean earlier I was doing like when I defined this p tilde, so just I mean you should remember that I mean earlier I was doing okay, so this is what we had defined earlier, which we called a Fourier transform, right? So that is a transform in from space, like x to theta. Okay, and now we are doing a transform which is more like a Laplace transform, right? Like if you have time, so this is n was the time variable, and now we are kind of changing from n to z. Okay. So this is like if you had a continuous function p of xt. I mean, you normally take a Laplace transform like e to the power minus st 0 to infinity. Right, this is then you can call it, let's say, p bar x of s. So you transform time to a new variable s by putting something like e to the power minus st, and so that's, so this function has that's exactly the same information as this function. And here you're doing something similar, except n was discrete, so you can't do an integral. So then instead of e to the power minus s, this factor e to the power minus s, you are putting some factor z, and then put zn and sum over all positive n. So n is time, so it's not going from minus infinity, 0 to infinity. So it's like a Laplace transform. So this is the generating definition of the generating function for the random walk. Okay, so the first thing we can do is it's easy to calculate. Okay, so given that we have solved this p of x bar n, then if you write the generating function, it looks actually quite nice, right? Because n occurs only here, and then we want to multiply by z to the power n and sum over n equal to 0 to infinity. So what will we get? So this we can, given p of x is this, we can immediately write the Green's function. So what will it be? I mean, can we, so we want to do the n sum. Right, so if you multiply by z to the power n and then sum n equal to 0 to infinity. Huh? Yeah, it's a geometric series. It's something to the power n equal to 0. So it's just a geometric series. So then you can immediately write. So this is just 1 by so that's the expression for the Green's function. And the other thing that you can do is you can start from this equation and then just multiply by, just like we were doing for the Fourier series, you can take this equation and multiply by z to the power n, right, and sum over n equal to 0 to infinity, and then look at, so you'll get various combinations, right? Z to the power n minus 1, you'll put some 1 by z and do all that. So we can do exactly like the what we did for the Fourier series, and you can get an equation for the generating function. So so I won't again do the details because it's you can just do it easily. But so basically, if you do this same kind of thing, so when you multiply by z into p x, let's say this one, so you have to put n minus 1 here and then multiply by z. So then this, you have to be careful that where it starts from 0, it's not minus infinity to infinity, right? It's 0 to infinity. So you have to be careful about some extra terms. Okay, so you have to add, so to get from 0 to infinity, you have to add some extra term and subtract. So if you do all that a bit carefully, then you'll basically get this equation. And this equation again you can solve just by Fourier series again and get this answer directly. So that's also one. Okay, so now let's see what this object. It has some. In some cases, it has a physical meaning. That's not right, right? Okay, so now if you take this genetic function and put z equal to 1, so z equal to 1 means you just sum this probability over all n. Okay, n equal to 0 to infinity. Okay, then this is the physical interpretation that gives the mean number of visits to the site x. Okay, so now I don't know if it's obvious. I mean, huh? No, sorry, what? Uh, okay, so basic idea is like this is the lattice, and you start from the origin, and you do this random walk. Okay, so you are walking. I mean, so you have reached here, then you keep walking, 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 and of course, eventually you will go up to infinity. But in the process, I mean, you can for a given realization, you can ask, you can look at various points and ask how many times did the walker visit. Right? At each, I mean, that's a reasonable question. I mean, like in this case, this point was visited twice, right? I mean, this is first visit, then it came back again. So 2 visits, and then it didn't visit. Okay. And some other points just 1 visit, some other point 0 visit. This is for one realization. Then you run over many realizations, and you can ask on an average how many times is each site visited. Okay, so what do you think is the answer? I mean, huh? The average number of sites each site is. So the walker keeps on walking forever, infinite time. One. I mean, okay, so I mean, so one thing you should not be confused is like P of x bar n sum over x bar. This is what? This is if I sum over all possible lattice sites. What is this? This is one, right? This is this simple. Okay, because this has to be normalized. 1 over total number of points. Total number of points is infinite or infinite lattice. So I mean infinite lattice. So it's 1 by no n is going from 0 to infinity. There's no n now, right? I mean this formula is there's no n. I mean you are waiting for like infinite time. The walker is walking, 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 and you just ask on an average how many times is a site visited. Okay, no, so less number of visits. Okay, that is okay. Right. Yeah, kind of correct. I mean, yeah, it's kind of correct, but it depends on dimension. Okay, and okay. So one question is how does it depend on dimension, and how does it fall? Like it's true. As you go further, it falls with the distance. Okay, so we want to ask how does it fall with distance, and that again will depend on distance. So that's what we want to compute. Okay, but now I said that this is that this object has this information that of the mean number of visits to this. So how do you see that this is true? Okay, is it obvious to anyone that this is true? It's not obvious, right? I mean, it's okay. So let's try to see. I mean, why this is true. Okay, so basically consider. Okay, so let me not just to simplify notation. Let me just do it for 1D random walk, and then of course it's almost the same argument for any dimension. So in 1D random walk, if you do capital N steps, all so n steps. So consider all the 2 to the power n. Uh, Okay, so if I have a n-step random walk in 1D, so then there are 2 to the power n possible different trajectories, right? And each trajectory means basically the position x is some function of time. I mean, so this is x as a function of n, and one trajectory could be like, that's one trajectory, and at each n I have x is specified. So x is a function of time, and it depends on the realization. Right? Each realization is some function of time. Okay, then I can write okay, so I mean, see, if I did a simulation, I would generate all the paths, okay, and then at a given time n, small n is a time which is between 1 to n, 0 to n, 0 to capital N, right? So at any time, if I want what's the probability it's at x, what I'll do is I will look at all, so there are various, I have to sum over all trajectories, right? So I look at all the trajectories where at the nth time, the particle is at x, right? And I just sum up all those ones. And if I divide by the total number of realization, I will get this probability. So I mean, if you have done Monte Carlo simulations, this is exactly what you do. Of course, you don't like this is too large. I mean, typically in Monte Carlo simulations, you will find that if you do a small number of realizations, you already get good answers. Okay, but this is a strict equality. So it's not an approximate result. This is strictly true. Okay, so this is this clear? Repeat. Okay. Okay, so I have a walk which goes from time 0 to some capital N. Okay, so this is one possible trajectory. And then I am interested in the probability that at given fixed time, some small n, let's say here, I'll find the particle at some position x. Right? So this is one realization where I found the particle. I'll run another realization, which might be maybe, so then the particle is not at this position, so that doesn't contribute. I'll look at the another part. I'll look at all the possible to the n trajectory. I'll just draw on this graph, and whenever it reaches at nth time, it is at this point. Those guys I'll just put 1, right? And then I just divide by total number of realizations, and this is what I should give me the correct probability. Right, so this is true. Now what I'll do is okay, so now let's take P of x n and sum over n equals to 1. So this is equal to okay, so I did this sum over n equal of n equal to 0 to infinity of this object, and then there were 2 summations, and I interchanged the summations. So I put the summation over small n inside. So then I get this. So now, and this n goes from 0 to capital N. So now, what is this object? So this is, I'm just now, a summation of a realization is outside, right? So this is for a given realization. If I do this sum, huh? No, it's not one. What is the physical meaning of this? No, so I'm looking at a given trajectory, and then I'm asking for that for particular trajectory, I mean, how many times was it one? Right, that's what it's counting. Like, I mean, how many times did it come to x? For a given trajectory, how many times did it come to x? No, it's counting the total number of visits to the site x for a given realization. Huh? So this is in a total number of visits to x in the given realization. See, because this, I mean, x point was visited at this time, it was also visited at this time, right? So in a given realization, how many times? 1, 2, 3, I mean, it was visited maybe 4 times, right? Yeah. You're asking this formula? No. Small n paths. Yeah. That was this, right? I mean, yeah. That will, so that is this statement. Okay, so this was for infinity, but I can put a capital N here. That is, so yeah, so here I put infinity, but now I'm trying to prove a statement for capital N. If I put capital N here, it gives mean number of visits to the site x bar till time N. Okay, and that's what I'm trying to prove. Okay, so I hope this is clear, right? This, how many people it's clear? I mean, okay, okay, at least some percent, okay. But anyway, again, this is the best way to understand this is, I mean, you just draw some trajectories and like I'm doing maybe n steps, but 2, 3 steps, right? And then just do all possible things, look at it carefully, you can convince yourself it's okay. Okay, so this is total number of steps in a given realization, and then I sum over all realizations and divide by the number of realization, and obviously that's the mean number of visits to a site X. So that's the proof. So, so therefore, okay, so now, and then if you put n infinity, you get this visit. Like the walker just keeps going on forever. Then you ask what is the mean number of visits to a site, given site. Okay, so now we have this formula. So we'll try to see if we can say something about like dependence on dimensions of this physical quantity. Okay, so so this was the expression for g of x bar z, and now we just want to put z equal to 1, okay, and compute this object, okay. So g, so number of this, okay, so z is gone now, and then it will be for okay, so this is the formula in any dimension. Okay, so now the simplest question maybe is like, what is like, okay, so this again is a difficult integral, but let's ask, like, I start from the origin. What is the mean number of visits I make to the origin? So I put x equal to 0. Okay, so mean number of, so visit means it's like returns, right? Returns. Okay, so I want to write x is equal to, so I just put x equal to 0. Now this is for return to the mean number of visits to the origin. Okay, so now let's look at it in various dimensions. Okay, so what is this integral? Huh? Okay, anyone knows what? It's a simple number, okay, I mean. Okay, I mean, so I mean, maybe you're trying to think if you can do it exactly, but even without doing it exactly, it's possible to say what is the answer. Okay, no, there's another simple number. Huh? 0, 1, okay. What? I mean, so if you should, when you look at an integral, you should think of like plotting it, maybe. I mean, if you plot this integral, I mean, obviously there's a problem at theta equal to 0, right? It diverges. So, okay, so, I mean, theta, okay, so let's say 0 to pi. On the positive side, you're plotting theta equal to pi, it's something half or something. And as you go to 0, it diverges. So then you have to worry, is this finite or not? Right? And so how will you check whether it's finite or not? You basically, you have to examine it near the origin, right? So you just expand this near the origin. So then this is what? Theta square, right? So this is approximately theta square. And this of course is what? Infinite, right? I mean, if you're doing 0 to something, This is infinite, right? At theta equal to 0, it diverges. So it is I mean just the integrand diverging doesn't mean the integral will diverge, but if it is 1 by theta square, it's definitely going to diverge, because you get when you integrate, you get 1 over theta, and that diverges at 0. Okay, so therefore this is clearly infinite. Okay, so in 1D, you come back, if you are on the infinite line, you come back to the origin infinite number of times. Okay. So that is kind of, again, because we talked about this polya problem, we said that you return to the origin with probability 1, right? So you return, and then of course again you go back, but again you come back, right? So because return of probability is 1. So therefore it makes sense, right? That if you wait forever, it will come back infinite number of times. So this is makes sense. And then in 2D, this G01 is equal to okay. So now what is this? Huh? This is also infinite. Okay. Everyone thinks it's infinite. Okay. So what is the argument? It's infinite. Yeah, it is infinite. So total return probability is 1. The return probability is 1. So it should be infinite. But from the integral, can you see it's infinite? Again, it's diverging at some places, right? So you again do expansion. So if you expand, then theta 2 by, so this 1 is important, right? Because then it kills the 1 from here, and you get theta 1 square plus integral. Okay. And okay, so you don't have to worry about the upper limits. I mean, near 0 you have to be careful. It's upper, you can put anything. Infinity is fine. Okay, so now, or let's put some pi. Okay, so now how do you do this? Polar coordinates, right? Yeah. So you can just convert to polar, and then you get theta d theta by theta square. So that's d theta by theta, and just one integral from 0 to a, and this is log theta. So that again diverges. Right? So in 2D also it diverges slightly slower. It's a logarithmic divergence. Okay, and so this is also. Okay, so and then okay, so here what do we do? It won't be infinity. Okay, yeah, why? Right, yeah. So this is now again you can try to of course it still diverges, right? The integrand still diverges near 0. Then you have to check whether it's integrable divergence or non-integrable divergence. Right? In this case, since it's 1 over, let's say again you go to polar coordinates, it's theta square, but then d theta 1, d theta 3 will give you a what? Theta square factor, right? Theta square d theta. So then this theta square cancels, and so there's no divergence. really at theta equal to 0. Okay, so in this case, of course, if it's finite, then you have to, then you can't, you can just replace it by the small theta limit. You have to actually sit and do the integral now. Okay, so that's why those integrals are in some sense easier. You can, it's infinite. But now here you can't make this approximation. At least you know it's going to be finite, definitely. Okay, so then you have to figure out how to do this integral. And you can do the integral and you get, of course, this is just a pure number. I don't know if I have the number. Okay, I don't have the number. I think it's maybe point. Huh? 0.6, is it? Okay, but anyway, yeah, that's what I remember. Something like that. Okay, so you'll get some number. So this is no, is it? No, I don't think it's 0.6. No, I think 1 by 0.6 maybe, but not. So it's some number. Okay, so this is the yeah, and okay, so now let's like it's clear that this should somehow be related to the return, the probability of return, right? So let's see, we can actually do it exactly relate this quantity to the probability that the walker will return to the origin. Okay, so okay, so. Okay, so actually you can write an exact formula relating this mean number of visits to the probability of return to origin. Okay, so let me just explain how to get this formula. Okay, so I mean, so basically, if you think about this this quantity, the mean number of visits. So the mean number of visits could be like you start from the origin, and then you do some number of steps, and then you come back here, right? So that would be one visit. Okay, or and then you after coming back, you could again go and come back here. So that's the second visit. So then the mean number of visits, G01, must be equal to okay, sorry, let me. Okay, so to find the mean number, okay, so what we do is you start from here, and one possibility is you you visit this site, return once, and then you never visit. Okay, so that would be the number of visits would be exactly once. Okay, and then you never visit again. Then there's a possibility that you come back here. So this is one. Then there's another path which like there are two visits and then it never comes back here. So and then so on. So therefore this I can write if it comes back once, so that is 1 times what is the probability it will never come back again. So that is okay. So maybe actually I should. Repeat. Okay, so let me say, so there's some one point I missed here actually. Okay, so I am trying to relate this and this object. Okay, so now I say that I can start from the origin. So that's when I count the number of visits, the starting thing is also counted as 1. So that if I never come back, that's like 1 visit, right? So I could start from here and then never come back. That's one possibility. Then there are paths where I maybe come back once and I return once and then I never visit again. Okay, and then there are paths where I visit twice and then never come back. Right? And what is the probability that I actually come back is what I called F. Right? This is the probability that I come back at any time. I don't say what time I come back. This is the probability that if I start from here, I'll come back. I keep walking. What is the probability I'll come back? That is what is F. Okay. So then I say this is probability F. Okay. So then I can write, I start from here and I never come back. So this is the probability that I never come back, 1 minus F. Right? Then I come back once. So it's 2, the probability that I come back once is F. And after that, I never come back, right? So that's 1 minus F. And then I come back like twice, and then I never come back, right? And so on. So I get a series, and so this series is this clear? Okay. See, this in the first path, the number of visits was 1. Right? I just started, that it was my, I was here, so mean number of visit is 1, then it never comes back. In the second one, I started 1, I came back 1, so 2 visits, and then I never came back. So that's why 2. In the another path, I would have like, so this I start is 1, I came back, that's 2, I came back again, that's 3, and then I never came back. So this 1, 2, 3 are the number of visits. And the other factors are the probability of that event happening. Okay, so on. And okay, so then this is a series which is 1 minus F. This is infinity now. I am just walking forever and asking when do I come back and what is the mean number of visits. When I said 0, 1, this is for infinite time already, right? Because n was summed from 0 to infinity in the Green's function, generating function definition. So everything is, time is now infinite time. Okay, so how do I sum this series? This is, okay. Huh? Right, yeah, it's like 1 n into x to the power n plus 1, some series like that. So you can, I think, so if you know how to sum, then if you take a derivative, that is, so that's the series, right? So we have to take dd f of 1 by f. So this is equal to 1 minus f. So that's the proof. Okay, so this is really useful because, I mean, so this is really the use of this generating function method, right? I mean, this is some object which is easy to compute. And then this was this is usually some very difficult object, with a return probability. But then you can relate these two and then you can compute this object. So now, of course, we can see immediately that in 1D, f is equal to 1, right? Because G is infinite in 1D. So f is 1. So the return probability is 1. So if you start from here, you'll eventually, if you keep walking, you'll eventually return. And 2D also it's 1. And 3D, okay, I don't know the number. I mean, so it's some number. Okay, maybe it's like 0.3 or something. So with probability 0.3, you will return. With probability 0.7, you'll just keep walking forever. Okay, so okay, so there's some sort of heuristic way you can understand this. Okay, so which is okay, but maybe I'll do it in the next class. Okay, so in the next class we'll now. So right now what we showed is that if you start from here, you will eventually return here, right? That's what we showed with probability 1. Now you can ask what is the probability I'll return here in time t. Okay, so I can ask for the distribution. So this is called the first passage time distribution. So okay, what is the notation? Maybe P1. So this is the return. What's the probability I will return to point x bar? Okay, so now it's a distribution in time, not in space. Okay, what is the probability I will return to? I'll go to a point x bar for the first time in time t. Okay, so this is a distribution in time. So if I sum over all time, this will give 1. Okay, so this is the next object we want to compute. And again, we'll see that using this generating function method, you can at least you can say quite you can obtain many interesting results, at least for large times and so on. Okay, so this we do in the next class. Any questions? Okay, reference I. Okay, so one place is okay. So there is a book called Statistical Field Theory. Okay. So they, I mean, it's a like it's a 2-volume book, but in the first volume there's a chapter on random walks, okay, which is kind of nice. And then okay, so then there's a this I can't remember. So by Sanjib, you're there now. Is there? Oh, do you know this? There's some article by Montrol and something. Montrol and Wise. I think it's a PA, right? It's a journal, right? Or it's this Dombe and Lebois. Dombe and Lebois. Montrol and? Okay, I'll give the exact reference later, maybe. This have to, but right, yeah. I mean, this doesn't have all this, but that's a very good, which is actually. I mean, this is, yeah. I mean, not all this you'll find there, but in general, this is a very good. 1942, right? Okay, so this is, huh? 43. Okay, so there's a Reviews of Modern Physics article by Chandrasekhar called Stochastic Processes in Physics and Chemistry. So I think that is really, I mean, a very beautiful article, and it's, and yeah, Feller's books. Yeah, actually, maybe that's a better view of it. I think in volume 1 you'll find this. So first passage is in volume 1, right? Okay, this one I'll give later. I don't know. So I mean, my thing is kind of I followed this book. Okay, but I think more or less it will be the similar. I mean, you won't find it. You'll find it in these two places, and maybe in Feller also. And Chandrasekhar is generally random walks, diffusion, and all. It's a really great article. Continuous case in time, right? Yeah. Yeah, but see there it's a bit tricky. Like if you in 1D it's okay. If you integrate over time, so you'll get the return product. Right? Yeah. But in you're talking about the mean number of visits. See there it's tricky. I mean because on a lattice you can really count the number of visits, right? But if you have a continuous process, I mean how do you? And in 2D, for example, if you ask what is the mean number of visits to a point, I mean, if you look at a trajectory, it will actually never visit a point. So you have to define then a domain, a small area. Then you can, then this is well defined and you can solve it using various other methods. Yeah. Yeah. It will gradually decrease, right? Yeah, yeah. Maybe it is this, okay, like this integral, if you do at large D, I don't know, maybe it's 1 by, you're saying as a function of D, is it 1 by D or something like that? Yeah, I think there's some, like for large D, you have some expression. I don't remember, but I can tell you tomorrow. There is some form, I mean, like the way it decreases. Probability of return is 0. Any dimension, infinite dimension, of course. Huh. Finite, I mean, you can have different lattices where you won't return, of course. Or like a biased random walk, then it may not return. But you can cook up processes where you never return, of course. Or lattices also, I don't know, lattices you'll always return with some probability. Unless it's like non-ergodic, means there's a, like, I mean, if you of course define a process where you can only take this, yeah, then of course, yeah, but if there is some chance, you'll always come back, right? I mean, there's always some problem. Dimension dependence of? Yeah. That's what in 1 dimension, 1, 1, and 3 dimension, 3 dimensions. That's what he asked, right? How does it depend on dimension? So for large dimension, there is some exact formula. In general, you can't write, I mean, because you can't do this integral for arbitrary dimension, right? And that is very hard. You can do it maybe for large D, you can do some approximation and do it. And for D equal to 1, 2, you can do it exactly. But in any D, of course, 3D also you can do it exactly. But there's no exact formula for any D. At least I don't know. Maybe some people have done it. I think, yeah, people keep doing this kind of integrals, mathematicians, and maybe someone has done it. I don't know. But large D, there is some formula. I'll tell you tomorrow. Okay.